Okay, let's have the second talk of this afternoon session. It's given by Professor Prabha Mandayam from IIT Madras. She's going to tell us about noise-adapted quantum error correction.
Thank you, Ganpathy, and thank you to the organizers for having me here and for putting together this very interesting and possibly one-of-a-kind program that brings together people from two apparently different fields. I'm afraid my talk is going to be of somewhat different flavor than the ones we've heard maybe at least today before. But also, unfortunately, I anticipate Serge's more detailed lectures on quantum error correction. So I will try to begin by giving a very quick and dirty introduction to quantum error correction itself, because I realize that we have a mixed audience here. And then I will talk about my main research work, which actually goes beyond stabilizer codes and looks at error correction in a slightly somewhat different approach to what one might call general purpose or standard quantum error correction. And then I will talk about the idea of noise-adapted error correction and noise-adapted recovery, and a certain map, a theoretical construct, which today has actually found applications beyond just quantum information and quantum computing, and actually finds application in many body physics, all the way up to ADS-CFT and so on. I will not touch upon all of that, but maybe mention some of those things. And then I will talk about some recent work with my students, time permitting, of course. I should also mention that two of my students will be presenting posters next week. So if any of this interests you, then you're welcome to go look at the posters for further details. Well, so just to motivate the next half an hour or so, today, as you know, we talk about this era of noisy intermediate scale quantum technology or quantum devices. We've had a very nice introduction to superconducting qubits, thanks to Vijay. But then he also spoke at length about some of the dissipative processes that these qubits undergo. And indeed, this is where we are today. Interestingly, this article was written in 2018, but I think this holds true even today. We are in an era with maybe not 100, but maybe 400 qubits, and they are indeed quite noisy. But I should also point out that it's not just the qubits that are noisy, but also the quantum gates that are noisy today. And given that it's very hard, it seems to be very hard to actually beat or keep increasing these coherence times, then it appears that we need to find some theoretical tools in order to increase the longevity of these qubits so that they can be actually used for some practical computing purposes. So that idea is indeed quantum error correction, and this gives us a hope that maybe such qubits can be scaled to actually form quantum processors or quantum computers. So let me begin at the beginning. So why do these quantum systems, why are these qubits so noisy? Why do we have errors? So at the heart of it is, of course, open quantum system dynamics. Many of us students probably used to thinking in terms of unitary evolution and closed quantum systems. But what this picture out here tells me that I have a system, my system of interest, which is probably a qubit. And it is indeed constantly interacting with its environment or its bath. And while this total system-bath interaction is modeled by a Hamiltonian and its dynamics are governed by some unitary operator, the system evolution in itself is not unitary. If I trace out these bath degrees of freedom, which I, perhaps as an experimentalist, do not really have control over, then the system evolution alone is non-unitary. And this is what we call a quantum noise channel, right? So just formally, this you can model as a certain kind of mathematical structure called a completely positive trace preserving map. So what do I have here? I have a system state, and I assume for convenience that initially the system and the bath were not really interacting. This is my bath or the environment state. And then together they undergo unitary evolution. But you see, typically this unitary is something that's going to entangle the system and the bath. And so although initially they were not correlated, this is going to cause some correlations and cause some information leakage from the system to the bath. And this is indeed what causes decoherence, dissipation, what you want to call it. Now, how do I formally write down the state after, or in a sense, due to the effect of this system-bath interaction? Well, I trace out the bath degrees of freedom. That's what I've done here. It's a partial trace operation. And what I'm left with is a map, is what we call a dynamical map just on system states. And this is sort of our starting point to understand decoherence in quantum systems, to understand what we mean by errors affecting the qubits. So Now, it turns out that such maps have a very simple and elegant description in terms of a set of operators. Today, they're commonly called Krauss operators, but I should point out that they should perhaps be called Choi-Sudarshan-Krauss operators. The physicist E.C.G. Sudarshan is one of those who had a role to play in understanding this kind of open system dynamics. And this set of operators become very important for us in the context of quantum error correction, because these operators are what we call the errors affecting the system state. So this rho out here is some system state, it's a density matrix, and E of rho tells me what happens to the state after it has undergone this unwanted or uncontrolled interaction with the bath. There are some constraints that this map has to satisfy in order for it to correspond to a valid physical evolution, but that's a mathematical detail which we won't get into. So here's a physical example. Here's a two-level atom sitting in a cavity, and we're all familiar with the unitary interaction. In this case, it's a Jaynes-Cummings Hamiltonian. So if I make this unitary, which I spoke about in my previous slide, if I make this U as a Jaynes-Cummings, the unitary that comes out of the Jaynes-Cummings Hamiltonian, then then I trace out the cavity modes, then what I'm left with is essentially what is called a T1 process. In the quantum error correction setting, this is what would be called an amplitude damping channel. And indeed, this entire process can be captured by these two operators. Those are the two operators that are sitting in this operator sum out here. This first, so let's just go a little bit into this channel because I'll be repeatedly talking about this channel. So let me talk about the second operator first. This is E1, and I assume I've written this in the bracket notation, but I can just write it out as matrices if that's something people are more familiar with. So my E0 operator is something that is diagonal in the eigenbasis of the sigma z, and the E1 operator is something that looks like this. This is an off-diagonal with just one of the off-diagonal entries out here, and this off-diagonal entry tells me that the excited state is going to decay down to the ground state with a probability given by the square of this quantity here. So the probability of decay is essentially gamma, and that's exactly this process that I've written out here. So the excited state decays down to the ground state with the emission of a photon with probability gamma. And the first operator out here, this E0, essentially completes the probability for you, right? You need the total probability of this event to be conserved. And this E0 essentially conserves the trace or conserves the probability because it captures the event that the excited state does not decay to a ground state. And that indeed happens with the probability 1 minus gamma. And if you were in the ground state, then nothing happens. That's what you call a fixed point of this map. So these two operators kind of capture this dissipation process. And this gamma is, of course, a function of time, although for the rest of the talk, I'm going to completely suppress this time out here. And I'm going to think about the gamma itself as a parameter that either characterizes the strength of the noise or that characterizes the probability with which my qubit is going to undergo this dissipation. But of course, this is a function of time, and this time constant is what we like to characterize in our experiments as the T1 time or the coherence time of the qubit. Now, I just want to point out that there's another setting where the same kind of channel, the same kind of two Krauss operator channel shows up, and this is a very different setting. So this work goes back to Saugata Bose in 2003. So this is actually a 1D spin chain, okay? And I'm going to now use this 1D spin chain as a kind of quantum channel. And I'm going to show you how I can use this 1D spin chain as a quantum channel. I'm going to think of one of these spins as a sender spin, and I'm going to encode a qubit worth of information in the first spin. And then I'm going to let the natural interaction of the spin chain take over. So the Hamiltonian that I will write down, for example, could be a 1D Heisenberg chain like this. And then as the natural Hamiltonian dynamics, so as the spin chain evolves under this Hamiltonian dynamics, I pick a different spin out here and I call that the receiver spin. And then I trace out all the intermediate spins, okay? And then I ask, what is the final state out here? So this process, it turns out, is exactly like what I had described earlier. I'm essentially thinking of the rest of the spin chain as forming a bath for the single spin, right? And it turns out, interestingly, that if you have a spin-preserving Hamiltonian like the Heisenberg chain, for example, then it turns out that the channel that you get has exactly the same form as what we called an amplitude damping channel. And of course, this has some interesting connotations because it means if I do some error correction for the amplitude damping channel, maybe that's something that I can use here to improve the fidelity with which this row out mimics the row in or the initial spin that I actually encoded. Okay, so this is just to tell you that there are different contexts where you can think of these quantum channels arising naturally under physical evolutions, right? Okay, so the example that I gave you is not an example that people normally quote when they talk about quantum errors. You typically have people talking about the sigma X and the sigma Z errors. So I will bunch all of them together and I will call them Pauli noise channels because these are Pauli errors. Now notice that the error that I've written out here, the model that I've written out here, looks nothing like a Pauli channel. In fact, of course, these are single qubit operations, so I can expand them out in terms of Pauli operators, but these do not admit very nice or simple expansions in terms of sigma X, Y, and Z. So just to complete the story, this will look something like sigma X plus I sigma Y, and this will look something like identity plus square root 1 minus gamma sigma Z. So these are not operators which just look like scaled X, Y, or Z operators. And that's what makes this kind of a channel more interesting for me than these Pauli channels, right? Also, these Pauli channels are perhaps not so naturally occurring in the physical systems of interest for us. But just to complete the story again, so this is what we call a bit flip channel. It says that this is what we call a sigma X noise, right? That the state of the qubit flips with a certain probability and does not flip with probability 1 minus p. And of course, this also, I think this was mentioned in one of the discussions yesterday, that you have a pure state. Suppose you start from a pure state, then what the action of this noise does is it decoheres you into a mixed state of this form, right? So you lose purity under this non-unitary evolution. So this is, of course, also a signature of the fact that this evolution is non-unitary. It is through this kind of a dynamical map. Okay, so let me proceed. These are just sort of the common channels that people look at. Like X noise, you can talk about Z noise. So instead of identity and sigma X, you can think of identity and sigma Z as being the operators of interest here. And that will give rise to what is called a T2 process that Vijay described also. And if you put all of these together, then you have depolarizing noise. This is what we call depolarizing noise in the error correction setting. So now how do you address this problem? So your qubit has decohered. You encoded a certain superposition, but then it, due to dissipation or due to T2 process, it decohered to a mixed state. So how do you now understand this, or how do you detect that such a process has happened, and how do you recover the information back? So, well, of course, you need new tricks in order to do this. When quantum error correction developed, of course, classical error correction was a well-developed field, so there were several tricks that were already in place, but then you had to adapt them to quantum information. So in particular, let me just give this example of a 3-qubit code. So what is happening here is I start with a single qubit, and then I map that via an isometry to a state of 3 qubits, okay? The idea is very simple, right? If I know that there is noise, I have to introduce some redundancy. So classically, it's very easy to introduce redundancy because you can just make copies. But then quantumly, you can't make copies. There is the no cloning theorem, which tells you that you cannot copy an arbitrary quantum state. So you have to circumvent the no cloning theorem. So you have to find also a unitary way of doing this. And I'll just show you a circuit which does that. So here's what a simple error correction circuit looks like. I have these 3 qubits. I started with 1, but now I have encoded that into a state of 3 qubits. Of course, some of you may recognize that this is an entangled state. If alpha and beta were exactly equal to 1 over square root 2, then this is what we call a GHZ state. So naturally, entanglement has come into play. And it is using entanglement that one is actually able to address or counter the effects of noise or decoherence. So you took this arbitrary state psi, and using these 2 gates, which I think Vijay discussed, these are the C0 gates, you prepare this entangled state of 3 qubits. Of course, now I must add that you assume that all of this is happening ideally, right? You assume that you have ideal C0 gates, and somehow until this point, your state hasn't decohered much. So I've put in a box here which says error. It's as if the error is happening after I have done the encoding, which is not realistic. But then what do? Now I also have this challenge of not wanting to break the superposition of these 3 qubits. So I do not want to directly, these M's here represent measurements. I don't actually want to measure these 3 qubits. These are what I will call my data qubits. These are the ones which I'm using for my computation. I don't want to break the superposition there. So I introduced 2 additional qubit registers, and these are called ancillars. And then I again entangle these ancillars with my data qubits, measure the ancillars. So the ancillars are like scratch pads, which I kind of write and reuse and or write and throw away, depending on how rich you are in terms of qubits. So you can always use them, measure them, and reset them, and again use them for the next set of error correction processes, right? So that's the idea. So you take that measurement information back here, and then you correct, right? So now this assumes that somehow these measurements are going to identify the errors for me. Now, not only do they have to identify the error, they also have to identify the location of the error, right? Now, both of these indeed happen in this case. So just want to point out that you've gone from what we call physical space, right, where I just had a single qubit, to a logical space of 3 qubits. But note that I'm not using the full 3 qubit space. I'm actually just using a 2-dimensional subspace of the 3 qubit space. It's an 8-dimensional Hilbert space, of which I'm just using a 2-dimensional subspace, because all the states I'm interested in are in the span of these 2 states. So this is what we call a code space, or a quantum code for short. So quantum code is just a subspace of a larger Hilbert space. And why does this work? Well, if your noise is just bit flip, which means it's just the X error, it's just the sigma X error, then you can sort of work out that individual qubits out here, or rather the set of 3 qubits, gets mapped to a set of orthogonal states, and orthogonal states can always be distinguished perfectly, and hence your errors can be detected and corrected. So the error correction relies on 2 things. One, that your errors map these states to orthogonal states, because that's when you can perfectly distinguish these errors. And second, the errors themselves are actually unitary operators here. Sigma X, sigma Y, sigma Z are all unitary operations. So I always can reverse them, right? So once I've identified where the sigma X error occurred, I can always reverse it. So these 2 kind of form the basis for standard error correction. And of course, you have to assume that the errors are suppressed in probability in some way, because otherwise your higher qubit errors will take over, and then this whole protocol will fail. So this is an underlying assumption that we carry through always. But I have just explained to you a code for a specific noise model, which is the sigma X error. Now, how do I deal with noise in general? Because in the quantum case, unlike in the classical case, where your bits either get flipped or they get erased, and that's pretty much kind of covers most of what happens with classical bits, that's not the case with quantum bits. Now, they can undergo a whole plethora of noise processes. Any CPTP map that I described, completely positive trace preserving map, is a valid quantum channel. So that's a continuum of errors. So I can indeed have erasure as well. Then I have this T1 process that I described. I can have T2, which I kind of club together with phase flip. I can have depolarizing and so on and so forth. So the standard approach is to discretize the errors. You discretize this continuum of errors into a finite set of unitary errors. And the Pauli operators naturally come to mind, because that's a finite set. That's a set of unitary operators. And what is more, they form a basis. So if I have a finite set of unitary error operators, then I'm done. Well, I'm not fully done, because I haven't told you that there's a linear theory of quantum error correction. Well, there is. So if I have a linear theory of quantum error correction, then any other error I can visualize as a linear combination of the Paulis, exactly like how I told you with the E0 and the E1 for the T1 process. I can break it into a combination of identities sigma Z, sigma X, and sigma Y, and hence use codes which correct for sigma X and sigma Z to correct for arbitrary errors. So this kind of leads us to the whole framework of stabilizer codes and so on. So you realize that this Pauli basis actually of n qubits, it forms a group under multiplication, but of course it's a non-abelian group. So then you consider abelian subgroups of the Pauli group, and you use that to construct quantum codes. I'm going to skip some of the details out here, because I hope that Serge is going to talk about a lot of this. But I just want to point out one thing here, that the group structure is actually at the heart of the error correction process here, because I have stuff that commutes, which are used to form the code space. And then there are operators that don't commute with this stabilizer group. Now, those will give me non-trivial outcomes when I measure my stabilized qubits. These qubits are stabilized under a set of operators. So the word stabilized means that they are left unchanged or invariant by some set of operators. Now the noise acts and takes them out of this stabilized state, right? And that the fact that I have Pauli operators that anti-commute with my stabilizer group gives me a set of errors that this code can actually detect and correct for. So as an example, this 3-qubit bit flip code that I mentioned is actually stabilized by a group that is generated by these two Pauli operators. These are 3-qubit Pauli operators. I have suppressed the tensor product sign, so you should read this as Z tensor I, and I tensor Z. So it's just a group generated by these two operators, and a common eigenbasis of this group is what constitutes the 3-qubit code that I showed you. Now it turns out that if you take this approach, you can put a bound on how many qubits do I need to correct for an arbitrary single qubit error. And it turns out that the shortest code that you can have is 5 qubits long, okay? But all of this assumes the perfect, so-called perfect error correction framework, where you want to perfectly detect and correct for these errors. But then, okay, so I also had a slide just to point out the connection to the toric code and so on, but I think I'm going to skip this again. Well, just to point out that the toric code is another example of a stabilizer code, except that you now have now qubits on the edges, and you have operators like this, operate tensor products. These are tensor products of 4 x's. This is a tensor product of 4 z's, and these kind of so-called vertex and placket operators form the stabilizer group. A common eigenbasis of this is actually 4-dimensional. It turns out that you actually have a pair of ground states if you write this many-body Hamiltonian. So this 4-dimensional subspace, which is the ground space, forms the quantum code for you in this case, okay? So this is, of course, many connections to many-body physics and so on. So let me just quickly summarize what I've told you about error correction. I've said that the code space is a span of a pair of orthogonal states which mimic your physical 0 and 1, but they are now states in a higher dimensional space. But essentially, it's a subspace of a larger Hilbert space. So I need an encoding operation. And finally, I need a way to put the information back or recover from the errors, right? In the case of the Pauli errors, this was very simple because the Paulis are just unitaries, and I just apply the same Pauli again and I reverse its effect, right? Okay, but now if I want to, instead of talking about perfect error correction, so when I say perfect, what do I mean? I mean that the final state that I get after the action of the encoding, the noise, and the decoding is exactly the same as the initial state. But that seems like a very stringent condition. That's a very high benchmark to set. So instead, if I were to allow for some deviation in fidelity, and what I've written out here is a fidelity function. This E is the noise map, the R is the recovery map, and the psi is the state of interest. So I have the state acted by noise and recovery, and then I take an overlap back with the initial state again, and I ask how high is this, right? I don't demand that this be 1, which is the case of perfect error correction, but I allow for some deviation in this, okay? But now, of course, I have to do this entire computation on the code space because I know that the bare qubit, I'm not going to be able to do any of this, right? I first have to go to a larger Hilbert space. So I have to do this minimization over the code space. I have to say, what is the worst fidelity that you can get over the code space? So this is a metric that we often use. It's called the worst case fidelity. And so we say that if this fidelity is exactly 1, then the channel is perfectly correctable on the particular code space. But if this fidelity is not 1, then we come to this class of what are called approximately correctable codes. So I think I have a picture which kind of depicts the difference between perfect and approximate correction. So this is just a cartoon which is telling you that I have my larger Hilbert space here. In the case of the 3-qubit code, this is the space of the 3-qubit is an 8-dimensional space. I have my code space sitting here, and E1, E2, etc. are the different noise operators. They are the different Krauss operators that I write down, which describe the noise map for me. Then in the case of a perfectly correctable code, these different errors have to map your code space to non-overlapping parts of the larger Hilbert space. And that is when I can perfectly distinguish this set of errors and I can perfectly correct for them. But what normally happens, if I were to pick an arbitrary subspace, if I were to pick an arbitrary code space, then this is what would happen. Or if I don't have this nicely structured Pauli noise kind of structure. But if I have something like this T1 process, then this is what is more likely to happen. I will have my code space getting mapped into overlapping spaces, which are deformed versions of the code space. They may not be unitarily deformed. They may be randomly deformed, like these kind of non-unitary operations. So this is what I'm interested in looking at, because this captures maybe a more realistic scenario, and it removes the constraint of perfect error correction. So it turns out that there are codes which actually mimic this kind of a property and still give you good error correction properties. So an example of that is this 4-qubit code. So I have 5 minutes. Okay. So I'm going to probably use the last 5 minutes to just talk about my work, but I'll just introduce this code and then I'll talk about my work here. So this 4-qubit code also has a stabilizer set, right? But it's not a perfect stabilizer code. I can't get into all the math out here, but in particular, it, for example, does not deform your code space unitarily. But it turns out that it can still achieve a pretty good fidelity in comparison to a stabilizer code. So the 5.1 is a stabilizer code. The 4-qubit, you see, I told you that the smallest error correcting code is only has to be 5 qubits long. But then here I'm giving you a pair of 4-qubit states. Of course, these are also entangled states. The first one looks like a GHZ and so on. I'm giving you a pair of 4-qubit states, which are achieving a fidelity, which is very close to the 5-qubit code. So this kind of motivates us to actually go beyond the stabilizer framework, to go beyond perfectly correctable codes. And many of the recent codes, which were probably even mentioned in some of the talks here, are all actually codes of this form. They are approximately correcting codes. They're not perfect codes. And indeed, they are, in many cases, tailored to this T1 process. Okay? All right, so let me move on a little bit, since I have just 5 more minutes. And I just want to talk about maybe just one thing. So if I were to now go into this framework of approximate correction, what do I need to do? How do I look for good codes? How do I look for the appropriate recovery process? So that's sort of the problem of noise adapted error correction or approximate error correction. How do I identify a good code space for a given noise model? And how do I identify the best recovery process for that noise model? I showed you this fidelity function. I could, of course, brute force optimize it numerically, but that's a triply hard optimization problem. It's a triple optimization problem and over a non-convex set. So this is a hard optimization problem. So what we initially came up with is an analytical solution for this. So we gave an analytical recovery map, which is simply constructed out of the Krauss operators of the noise channel itself. So these are the operators of the noise. This is your code space. Now the code space, when I define the subspace, I have a projector that characterizes it. So these are the two inputs that go into defining this map. So for any noise model, Pauli or non-Pauli, even something like this, I simply have to write down this recovery channel. And then we have a proof which says that this achieves a pretty good fidelity for any, it achieves a pretty good fidelity provided the noise and the code space are actually close to approximately correctable. So this map, so let me just phrase this, state the correct statement. So it achieves a fidelity which is close to that of the optimal recovery channel. So if for this pair, I have an optimal recovery map which is going to achieve very good fidelity, then this theoretical construct will give me close to optimal fidelity. So this is a very useful theoretical tool. Today it goes by the name of the PETS map. And a lot of my research has focused on understanding this map and also more recently coming up with a way to implement this map. Because for the 3-qubit code, I showed you a nice quantum circuit which actually does the encoding, which does the measurements, it does the recovery and so on. So can one do the same for this kind of a map? Now it turns out that that's actually a hard problem to solve, because what I've given you here is a quantum channel. I've not given you a unitary process. I have given you a dynamical map, which is like the noise map in some sense. So how do I come up with a circuit construction of this? So that's one of the pieces of work. So let me skip all of this. So just want to point out some interesting structures for this map. So it turns out that this map, which I showed you, can be decomposed into a set of 3 maps, none of which is actually implementable by itself, none of which is actually physical by itself. In the sense, by physical, what do I mean by saying it's not physical? I mean that each of these individual maps need not be trace non-increasing. Okay, they could be trace increasing, and those are not physical maps. But it turns out that the composition of these three maps is actually trace preserving, right? So, or rather trace non-increasing. So I just want to say that this is work with my students. So this student Devjyoti who's here, and he presented a poster on this where we, so this is work that's also on the archive, circuit implementations of the PETS map. So we use some interesting algebraic techniques to actually arrive at circuit implementations of the CPTP map. If you're interested, find me after the talk and I can tell you a bit more about any of these, or you can talk to Devjyoti and he'll tell you about these. So you can do something called an isometric extension, you can do a POVM, you can do block encoding and so on. But I just want to show you some results that we have. So this, what do I plot here? I plot the theta out here parameterizes my initial encoding for me, right? This is a single qubit state, which I'm now encoding into this 4-qubit code that I showed you. And then I implement this PETS recovery map. And what I plot out here is the fidelity function. And this here is the unencoded qubit, right? This is how the unencoded qubit behaves. The 0 state, like I said, is a fixed point of the map. Remember, the map that I'm looking at is this P1 process, right? And the ket1 state, which is here, the fully excited state, is the one that decoheres maximally because it's going all the way pi on the block sphere, right? So this is how the fidelity would fall if you did not do the encoding and the recovery. But these are the curves we get if you do the 4-qubit code and the PETS recovery circuit implementation that we worked on. So these have been implemented on the IBM qubits. So this is a simulation. This is also a simulation, but this is now a noisy simulation on IBM. So what you can do is you can actually inject some noise. So we did, of course, try to run this on the actual qubits themselves, and they were too noisy for these circuits. It turned out that they decohered very rapidly. So they were actually not even long-lived for us to have a good encoding in the first place. So instead, we went the other way around and we asked, how much noise can this encoding and this circuit implementation of the recovery actually tolerate? So we actually come up in our paper with a threshold for how much C0 noise our protocol can take and how much single qubit noise our protocol can tolerate. So this again is the unencoded qubit. These are all the error-corrected qubits. You see the fidelity is always above a 0.8, whereas normally you have this kind of a sharply decaying fidelity profile if you don't do error correction, okay? Fault tolerance is not something that I'll touch upon. This is, again, we quantify the resource requirements and so on for these circuits. So let me just jump off to the conclusion slide and summarize. So I hope I have communicated to you that noise-adapted error correction can provide a good degree of protection from the dominant noise process affecting the physical qubits. I say dominant because I assume that I have a physical architecture like, for example, superconducting qubits, where the T1 noise process is native and dominant and not a Pauli noise like X. So in such cases, we believe that these kind of noise-adapted protocols might help better than standard error correction. There are some nice connections to many body settings, which I haven't really had the time to tell you about. I also want to mention that we extend some of our constructions for QDIT, which is the higher dimensional quantum states, and a similar kind of dissipation. You can think about these jumps happening from higher levels as well down to lower levels. You can think about a higher dimensional amplitude damping channel. And again, there's a poster by my student next week. So thank you for your attention, and I'm happy to take questions.